yesterday. So, and we talked about it in length, but I'm going to recap so we remember a bunch of things. If you have an opening A and light is coming in, the plane wave's coming in from that direction. You remember the location of minimums, and of course you're going to get a pattern like this. And these are the minimum locations of minimum. First, minimum, second, and so on and so forth. And if you remember, location of minima locations are given by the equation A sine of theta equals m lambda, where m is either 1 or 2 or 3 and so on. Okay? So this is for m equals 1, m equals 2, m1, m2, and so on. And the angle you're talking about is this angle. The angle theta is the angle to these minima or maxima. So the angle is measured in that direction. Same angle, of course, this way as well. All right, so this equation means this thing in when you're talking about diffraction. This is the location of minima. So remember, this is the minimum locations. Okay, and if you remember, without proof, we also said that intensity of light as a function of that angle theta is some maximum sine of alpha over alpha squared, where alpha was defined as 1/2 the phase shift, which is pi over lambda a sine of theta. Okay, so this was also, and this is the shape of this curve. It's the shape of this curve. It's this function. All right, so how about the location of maxima? So far, we could find the location of minima pretty accurately. And we have this equation that shows the actual functional form of the intensity on the screen. From this equation, you can actually get the location of the minima directly from the function by setting it equal to 0. And you will get exactly the minima that we have written on the top. Okay? How about the maxima? How do we find maxima? Well, you can always take the derivative of the I of theta as a function, with respect to theta, and then set that equal to 0 to find your maximum and minima. And then you have to decide which ones are maximum, which ones are minimum. But there is a better approximation to finding the maxima. So intensity versus theta. Again, it's going to look like this. And we already know these locations. This is the first one. So if you remember, A is sine theta and lambda. So this is where m is equal to 1. And so and alpha is 1/2 phi, which was pi lambda over a sine of theta. And so when m is equal to 1, a sine theta is just lambda, and alpha becomes pi. And alpha here is 2 pi. Alpha is pi, alpha is 2 pi. Remember, alpha is defined up there. And this is the location of minima. So when m is equal to 1, this is m equal 1. M equals 2. M1, M2. When m is 1, a sine theta is just lambda. You plug it into alpha, and then you get pi. If you do the same thing for m of 2, you get 2 pi for alpha. Okay, so, and maximum locations. Now, how about maxima? Well, first of all, the main maximum location is right at theta equals 0. And that's obvious. Okay? But how about the other ones? These other secondary maxima. What are these? Again, there are two ways of doing it. One, you can take the derivative with respect to I of theta and set it equal to 0. And that will give you the location of both minima and maxima. It gives both max and minimum. But that's a little bit too complicated mathematically. So a good approximation is halfway between minima. Okay, so that's a good approximation. If I find halfway between the minima, that's roughly the maximum values. All right, so for example, the first secondary maximum, not the main one at 0, the first secondary maximum, maybe I should write it, secondary max is halfway between the minima. So 1/2 of 2 pi plus pi. Okay, so the halfway is 3/2 pi. Okay, and the secondary max is halfway between 3 pi plus pi, 2 pi. That's 5/2 pi. So you can see I can write the location as m plus 1/2 times pi, where m is equal to 1, 2, 3, 4. You get these numbers. So this is the location of approximately maximum locations. Okay? So now you know where maxima and minima are for this intensity of a diffraction pattern as a function of angular separation. Real physical separation depends on how far you are, but the angular doesn't. Angular is just angular. Guys, have any questions? Now, one other thing we can do is to calculate the intensity of light. So let's go back and find out what is the intensity at these locations. Okay. Again, it'll look like this. Now, if you remember, the equation for this thing is I sub m sine of alpha over alpha squared, where alpha is 1/2 of phase shift, which is pi over lambda a sine theta. And so therefore, this location, which is maximum, is I sub m, which is this part of the equation here. All right, so with respect to that maximum, what are the secondary maxima locations? So what is this level, for example? What is the height of the secondary maxima? Right, if you remember, these secondary maxima locations were pi m plus 1/2, and so this first one is just 3/2. And this one was 5/2, and so on and so forth. So this is 3 pi over 2, and then 5 pi over 2 here as well. All right, so if I know that that's the case, that's the location, I can just plug it into I can just plug it into the equation and find out. So I, for say first max, is equal to Im, and then pi over 2 becomes sine of pi 3/2 pi 3/2. Which is roughly Im times this. Okay, so that's let me take a look here for a second. So that's the location, that's the magnitude. So you can see how much, it's only 4.5% of maximum center, which is huge. It's huge. It's extremely small. It's a huge reduction, I mean. It's extremely small. So it's really, really small if you look at it. Whoa, what happened? Okay, so it's really small. These are, by the way, alphas. So you can see the reduction is huge. The second maximum is at the location of only 0.45 times I of max, right here. So you can see it's enormously small. So the actual thing would look something like this. Whoa. So if this is the maximum at this center, if this is Im right here, which what that equation says, the second one's only, you have to multiply that by 0.045. So you can see it's like tiny. It's extremely small. And the other one's even smaller. And you can calculate the other one. So this one is at IM. This is at 4.5% of IM. And you can calculate the next one. And when you calculate this next one, it is 0.016 of IM. So you can see how hugely suppressed these other maximas are. So whenever I draw it, anywhere else before, it looked like those are really large, but they're really, really small. The main peak is that's why it's called the main peak. The other ones are just tiny. You can see it. It's a really it's a huge reduction in amplitude of that secondary maxima. Okay, they're really small. All right. So far, any questions, guys? Okay. All right. Now, let's go back to the diffraction again. This time, this is a circular opening. Okay, it's a circular opening. So if you remember, for a slit, for just a regular opening, the first minimum was when a sine theta is equal to lambda. We just did that. This is the case where m is equal to 1, the first minimum. So this angle for first minimum is just lambda over a. Okay, this is the first minimum. So and it looked like this, in one dimension it looked like that. That's the first minimum. Now, what happens for a circular opening? What about here? Now, the mathematics is pretty complicated. So so in a circular opening, the thing still looks very much like this. But because it's circular, the actual screen looking face on would then show you a main circular spot. Okay. Instead of being those slitty looking things, now it's a circular spot. And then you have the secondary maxes around it as a ring, and so on and so forth. So, and then you have another one. And so this is face on. Okay, but then the angular position of the first minimum, this is theta of the first minimum, is slightly different when you do the math. So it's not a sine theta, and a, of course, is the diameter this time. This thing was a, this is a, or we can call it diameter so it's not confusing, d for diameter. Okay, so it's not exactly a sine theta equals lambda, but it turns out to be d sine theta equals 1.22 times lambda. So for a circular opening, the first zero is not the same as a as a rectangular one. Okay, for a circular one, it's slightly off. So even though they look the same, their numerical factors are different. Okay, so that's the location of the first minimum. That's the theta of the first minimum for a circular opening. All right, and you already know that the secondary maxima are pretty weak. So even though I've drawn them like that, the secondary maximas are pretty small. So essentially what you're going to see is a circular middle one, and basically that's it. Very, very faint secondary maxima. That's what you're going to see in reality when you look at the diffraction pattern of a circular opening. Okay? Now, all right, so suppose I have a circular opening. Okay? And suppose far away there is a point of light. It's a point light source at the very far away distance. Okay? That is going to produce some waves. They're, of course, spherical waves. But because I'm so far away, by the time I get here, they're pretty flat and plane wavy. Now, plane wave goes through a circular one, and it will produce a diffraction pattern on the screen that'll look like this. And we already know that. Okay, so that's the diffraction pattern due to that light source 1. And suppose there is another one somewhere else. And that one also is shining its light out, which comes out at spherical waves. But we're so far, by the time it gets here, it's pretty flat. And that will also produce its own diffraction pattern on the screen. All right. Now the question is, well, this circular opening is roughly the model for a camera. Okay, this is roughly a model for a camera. Now, a camera has a lens, and it has a diameter, and whenever you have an opening, whether there's a lens there or not, it doesn't matter. The actual pattern will be a diffraction pattern. So any point source of light will have to form a diffraction pattern on the film behind the camera. And it won't be exactly a point here. It would be a diffraction pattern shape. So that, we did study image formation in lenses. In fact, we took our first quiz on it last week. And the way we have always learned how to deal with lenses was through ray optics. And of course, if you use ray optics with this thing, with ray optics, you say, all right, this is my image. and it's going to go like that, and something else like that, and it's going to form an image on the other end, and there. That's my image, and that's my object. In reality, if it's a point source, it is going to be an image of a point source. So if it's a point, it would be a point. And if it's truly a point, it won't be a true point here. What it would be is the diffraction pattern for that point. So that's really the image here. Because the lens has a finite diameter, the point source will have to form a diffraction pattern on the film. So the point would not become a point. Well, in ray optics, it is a point. But in reality, when you take into account diffraction, it becomes a spread out kind of a smear point, not an exactly one point, which is that diffraction effect. All right. So if I then have two point sources, I would have another diffraction pattern on the film, just like the one I've drawn on the top. And the question is then, if this camera is looking at these 2 points with this angular separation, this is the angular separation between the two, this is the angular separation. Between the 2 points, how close can they be in angular positioning, angular separation, before the two diffraction bumps on the film are not distinguished as two anymore? Okay? So obviously, if the angle gets too close, if theta is too small, what you see on the film is the diffraction of the first one and the diffraction of the second one. And when you add these two, in reality, you would see a thing like this. And so if you see a thing like that, you don't know what you're looking at. You don't know that these are actually 2 points. So the question is, what angular separation should they have before you can actually tell what you're looking is actually 2 points? Because right now, if it's too small, I'm looking at this and I go, if I look at this and I go, what is that? That doesn't look like 2 points. It looks like one bump. So then I don't know that there are actually two of them. So the camera cannot, what they call it is, the camera cannot resolve. It doesn't have enough power to resolve that the 2 points are actually 2 points. It would record only one bump there, and it completely misses the fact that there are 2 of them, but they're just too close to each other. So you really need something that produces 2 bumps that are quite separated from each other, because when you add these two, then you get something like that. And if that's what you see, then you know. This is obvious. This is easy to see. There are 2 points. Okay, but when they get really close, then when you add these two, you get something like this, and you can't tell anymore. So, not able to distinguish 2 sources. So what is it then? What is the minimum criteria? This is, by the way, called Rayleigh's criteria. Okay? So what is Rayleigh's criteria? Okay? So Rayleigh's criterion is they need to be separated. Now, if you go back to what I was talking about here, you can see that the first minima happens for a circular opening at this equation d sine theta times 1.22 lambda. So the criteria to distinguish it is that they should be at least, the two peaks should be at least that much off of each other in angular positioning. That's what Rayleigh criteria is. So you want, so if the first peak is here, and you want the second, and this is the position of the first zero, so this is theta 0, and this one is given by d sine theta 1 equals lambda 1.22 times lambda. Okay, so you want the second one to be, the closest they can be is if the second one is peaked right here. Okay, so this should be the minimum. This distance here, which of course is given by the distance between the two, and you know, if the angle is too small, this makes the angle very small. So we can then say sine of theta is roughly equals to theta. Then I can say d theta is 1.22 lambda. Okay, so that angle then is roughly then 1.22 lambda over d. This is the separation between the two. So this is delta theta. This is the separation delta theta, because it's measured from 0, right? Delta means the final minus initial, but final is that, and initial is 0. So this is the theta. So the angular separation between the two point sources, when they form a diffraction pattern on the observation screen, needs to be at least this much. If it's any smaller than this, the two peaks will merge to each other, and you can't tell the difference anymore. Okay, this is called Rayleigh's scattering. I mean, Rayleigh's criterion, sorry. There is a Rayleigh scattering, but not in this class. Okay, so you can see the peaks need to be at least this much or larger before the system, like a camera or a microscope or telescope, can distinguish that there are two of them. So far galaxies that are filmed with a telescope, if they're too close in angular separation, they cannot be seen as two galaxies. You can only see one spot, and you don't know what is going on anymore. Okay, that's why most telescopes have a large diameter collection lens, because of this equation. The larger d is, the smaller angular separation you can resolve. So the larger the aperture of the collection of the telescope is up front, the smaller angular resolution you can see really close heavenly objects, and you can resolve them into two peaks, and you say, there are two things here, not one. All right. Where are we? Okay, so that's Rayleigh's criterion. All right. So far, let me so far, all right, so far, we know if we have two tiny points of opening in a film, they form interference. And you remember that, right? We had peaks and valleys that will form interference pattern. And we did that, and the location, and if you remember that, let me write it down. To remember, the location of that thing was location of the maximum minimums, or given by and your intensity was okay. So you could tell, if you remember, we had two beams coming in, and the difference between the two was d sine theta. And if this difference was a full, if it was a full wavelength, you would get a constructive interference. If it was half of it, you would get destructive, you would get maximum minima. And we calculated all that stuff. This was like last week or maybe a few days ago. And so we already calculated that, and we got an interference pattern. Then we also learned, so this was interference pattern. Then we found out that we get diffraction as well. Diffraction was one opening, and on the screen you would get a diffraction pattern, right? That's what you would get. And the diffraction pattern gave us another equation for when alpha was pi a over lambda sine of theta, and the interference pattern had an equation. Diffraction pattern had an equation as a function of theta as pi m sine of alpha over alpha squared. Okay, so far, this is what we've learned. Diffraction pattern due to two slits, and diffraction pattern an interference pattern due to two slits, and the diffraction pattern due to one slit alone. Both are showing you the wave properties of light. Okay, otherwise you wouldn't see any of these patterns. After all, we're saying, hey, if the wavelength moves by one wavelength, they interfere constructively. All of this thing is only a wave property of the light. Okay, but what if we have, going back to two slits, in reality, even the two slit experiment shows diffraction. Okay, so the thing that we drew on the top, which was the interference pattern, because now we know diffraction, which is just light going through one single opening, produces a diffraction pattern. Therefore, we have to go modify our interference, because each of those openings should produce a diffraction pattern as well. And so the way this thing works is you actually get an envelope for diffraction pattern. here. So this picture on the top is really not correct. In reality, what you see is this. Okay? So the envelope, so okay, let's give these numbers. So this is A, and the opening is, I'll just D, and the opening is A. And so what happens is the diffraction is produced for each of those holes, and then there is interference on top of it due to having two of them. And so you will get a large envelope that's due to diffraction due to one of those openings. And you then see an interference pattern inside that envelope that is due to the good old interference on top. And so the intensity you get at the end is the intensity of those two multiplied by each other. Interference times intensity of diffraction. And that's easy to see. It's I sub m. Cosine squared of beta, and then sine of alpha over alpha squared. So that's what you really see. So this is really the correct form of intensity for any 2 points that produce not only interference, but each of those openings on itself produces a diffraction pattern. Okay? All right. Now, you need to be careful with this thing. Because these two functions are multiplying to each other, the first zero of the diffraction will suppress whatever's at the position due to the interference. So let me emphasize this, because this, I don't want this to be a source of confusion. So the envelope is this. So the actual pattern was like this. Okay, so it goes in something like this. Okay, so, and you can see the envelope. You can see this envelope of the diffraction pattern. Okay, so this is what you see for two slits, but diffraction wins. Diffraction wins. What do I mean by that? If the formula for diffraction forces a zero here, if it forces a zero here, intensity is zero. Even if interference pattern has a maximum here. Okay, so if you go back to the calculation and go, that position has to have a maximum due to the interference, the diffraction says, sorry, according to diffraction, that point is zero. So diffraction wins. But that, you can see that from the equation. I mean, it's nothing weird because mathematically we're talking about two functions that are multiplied to each other. Obviously, if one is max, the other one is zero, the whole thing becomes zero. So it's not strange. I'm just saying what this equation is talking about. Okay, if the cosine is zero, it doesn't matter what that other form is. If it's max or min, doesn't matter. This whole thing is zero. That I'm just writing what an equation will tell you. Okay. Yeah. What's what? Theta? Oh, okay. Yeah, I wrote it down here. There. Yeah. So it looks just like alpha, except d is the distance between those two, but in alpha, a is the diameter of the opening, or width of the opening. But they look identical in form. If you go back to what we did with interference, you'll see that this is beta. Okay. Any questions? Oh, we're out of time. Let me get a screenshot. All right, guys. I will see you tomorrow. Take care.